Welcome to the explainer. So, hydrates aren't actually ice, but man, they behave exactly like it. We're talking solid, crystalline structures capable of forming inside a warm looking pipe so fast they can completely block flow in a matter of hours. And listen, this isn't some slow degradation problem like pipeline corrosion. This is a sudden, acute event. If a hydrate plug forms in the wrong place, getting rid of it can take weeks and cost literally millions of dollars. Honestly, it's the ultimate deepwater menace, and it is absolutely the threat that keeps flow assurance engineers up at night.
To kick things off, let's think about a pretty critical question. When do you think a deep water pipeline is most likely to freeze solid? You might intuitively guess the risk is highest when the pipe is actively doing its job, when massive volumes of fluids are flowing through that dark, freezing environment on the seafloor. But it turns out that's a massive misconception. The actual danger zone? It's right after an unplanned shutdown. A completely dead shutdown pipe is where the risk just absolutely skyrockets. See, while flowing, the warm reservoir fluid actually keeps the pipeline temperature well above the danger zone. It's the exact moment that steady flow stops that the true race against time begins. To really get why this happens, we need to dive into the chemistry.
All right, let's get into Section 1, the ice that isn't ice. So what exactly are we dealing with here? Natural gas hydrates are crystalline water structures. Basically, they form when water molecules trap low molecular weight gas molecules, like methane, ethane, or hydrogen sulfide, in this sort of ice-like cage. But here's the kicker. For a hydrate to actually form, you absolutely must have four specific elements present at the same time. You need water, you need that light hydrocarbon gas, you need low temperatures, and you need extreme pressure. If you take away even one of those four things, a hydrate simply cannot form. Now here's where the deep water physics get incredibly counterintuitive. We all know regular ice forms at 32 degrees Fahrenheit, right? Normal atmospheric pressure, 0 degrees Celsius, boom, ice. But deep underwater, the pressures are immense, thousands of pounds per square inch, and that completely changes the game. Under those intense pressures, hydrates can actually form at temperatures well above freezing. We're talking sometimes up to 70 degrees Fahrenheit. To us, that fluid feels perfectly warm, but under thousands of psi, the gas and water are basically forced into that crystalline cage, creating a solid block of ice right inside a warm pipe. Crazy, right?
Moving on to Section 2, the subsea ticking clock.
Okay, so as soon as an unplanned shutdown hits, the clock starts ticking. Step 1, steady state flow totally stops. All that friction and continuous heat from the reservoir, gone. Step 2, the fluid just sitting dormant in the line starts rapidly losing its heat to the ambient seawater, which is sitting at a relentless 40 degrees Fahrenheit. Step 3, as the fluid cools down, the operating temperature and pressure suddenly cross over what we call the hydrate formation curve. And finally, step 4, hydrates rapidly form. And because the whole system is fully pressurized, you don't just get a little bit of slush, you get a massive solid plug that completely grips the walls of the pipe.
Because this cooldown sequence happens so fast, engineers rely on a very definitive metric called no-touch time. Basically, this is a calculated countdown, often just a few hours long, before the cooling fluid hits that critical hydrate formation temperature. It's called no-touch because during this brief window, operators get a sort of grace period. They can troubleshoot the platform trip and try a warm restart without having to resort to drastic, expensive chemical interventions. It gives them a hard deadline. Once that no-touch time expires, you have to act immediately, or you are going to lose the flow line.
Which brings us to Section 3, salting the deep water road. You know when they salt the roads on a freezing winter morning? Pure water freezes at 32 degrees, but if you dissolve enough salt onto the road, it actually drops the freezing point of the water, so the road stays wet and liquid at temperatures where it would normally just be a sheet of solid ice. This is a concept called freezing point depression. Well, subsea engineers do the exact same thing to flow lines, using thermodynamic inhibitors like MEG, monoethylene glycol. By injecting MEG into the pipeline water, they fundamentally shift the hydrate formation temperature lower, pushing the fluid back into a safe liquid state.
These thermodynamic inhibitors, or THIs, are pretty much the industry's brute force, old reliable approach. They physically grab that hydrate formation curve and shift it to lower temperatures, which gives you a much wider, safe operating margin during a shutdown. But there's a catch, and it's a big one. To get that shift, you have to pump in incredibly high dosage volumes. We're talking injecting MEG at 10 to 60% by weight of the produced water. That requires a massive chemical footprint. You need huge, expensive topside regeneration infrastructure just to boil off the water and recycle the MEG. It works, for sure, but it's a huge logistical and financial burden.
Let's check out Section 4, the chemical arsenal. Okay, let's stack these strategies up against each other. On one hand, you have your traditional THIs, the curve shifters that require all that massive topside infrastructure. But on the other hand, you have low-dosage hydrate inhibitors, or LDHIs. Instead of pumping in 10 to 60%, LDHIs are injected at less than 1% by weight. So your system footprint shrinks from a massive regeneration facility down to just a few small injection pumps. But here's the thing, their primary mechanism is entirely different. LDHIs do not shift the curve at all. They just delay crystal growth or prevent sticking, and their protection is strictly bounded by specific temperature limits.
So how do they pull this off with so little chemical? Well, there are two types of LDHIs we need to look at. First, kinetic inhibitors, or KIs. These are basically water-soluble polymers that bond to the surface of a forming crystal and just artificially delay its growth, which buys the operators more time. Second, you have anti-agglomerants, or AAs. These act like a sort of non-stick coating. They actually let the hydrate microcrystals form in the pipe, but they coat them so they can't stick together. The fluid turns into a slush, sure, but it remains totally pumpable. So both of these act as a clever chemical shield rather than a thermodynamic cure. But listen, this is super important. LDHIs come with a massive operational warning label. Because they don't actually shift the thermodynamic curve, they have a strict, limited protection window. Kinetic inhibitors will typically fail completely if the subsea temperature drops more than 20 degrees Fahrenheit below the hydrate curve. Anti-agglomerants might buy you 40 degrees, but if you try to apply them outside their strictly qualified limits, or if a shutdown just drags on too long, that temporary chemical shield breaks down. And when it does, all those suspended crystals will suddenly snap together into a catastrophic permanent plug.
And that leads us right into Section 5, the last resort.
So what happens when a shutdown extends indefinitely and you're out of options? Engineers have to execute a highly stressful operational maneuver called blowdown, or depressurization. Step 1, they bullhead, meaning forcefully pump neat methanol down the wellbore to protect the most critical safety valves. Step 2, they open the topside valves to deliberately depressurize the entire subsea flow line. Remember, extreme pressure is one of the 4 mandatory elements for a hydrate. By venting the gas and dropping the pressure completely below the curve, you destroy the environment keeping the crystal stable. Then, step 3, if a plug is already there, you drop the pressure and you just wait. Sometimes for days, waiting for the tiny amount of heat in the 40-degree ocean to slowly melt that plug from the outside in. Why go through all this stress? Well, besides the fact that a flow assurance engineer is probably sweating bullets, it comes down to millions of dollars. If a plug forms and depressurization fails, which can happen if the heavy liquid in a deepwater riser prevents the pressure from dropping low enough, you are officially in a nightmare scenario. You can't just call a plumber. You have to mobilize heavy subsea intervention vessels. They have to physically tap into the line, inject hot fluids, or literally cut out the plug section of the pipe. You're looking at weeks of lost production, and the vessel day rates alone will bleed millions of dollars from the project.
So if you take one thing away from this entire explainer, it should be this. A field can flow perfectly safely for years and still form a catastrophic hydrate plug during a single, unplanned shutdown if inhibition isn't triggered fast enough. Hydrate risk isn't some steady-state wear and tear problem. It is fundamentally an acute, event-driven threat. A perfectly healthy, multi-billion-dollar subsea system can be completely paralyzed in 8 hours flat if a platform trips and the thermal insulation and chemical systems don't immediately do their jobs. To wrap things up, I want to leave you with a bit of a provocative question about the future. As subsea tiebacks stretch further and further into the freezing, ultra-deep-water abyss, connecting reservoirs that are miles away from their host platforms, the cool-down times are getting shorter and the pressures are getting higher. Will our current chemical arsenals of MEG and low-dosage inhibitors be enough to keep the flow alive? Or are we going to be forced to invent entirely new ways of actively heating the deep-sea floor? It's a massive engineering frontier. Thanks for joining me on this explainer, and keep questioning how things work beneath the surface.